Hi class, in this lecture we're going to move into our next chapter talking about partial derivatives. And before we can get into the concept of partial derivatives, I want to move into this first section talking about functions of several variables. So I'm going to introduce this concept of function of several variables with an example. Okay, so suppose the temperature T, okay, that's what you're trying to find, at a point on the Earth's surface at any given time. Okay, so like suppose I want to find the temperature. I live in Morristown, New Jersey. I want to find the temperature of Morristown, New Jersey right now. Well, that depends on the longitude and latitude of that point. Okay, like the temperature here in Morristown, New Jersey is going to be different than the temperature in Valhalla, New York. Okay, so it's going to depend on the longitude X and the latitude Y. So we can think that temperature T as being a function of two variables. It's going to depend on your longitude and latitude, or as a function of the pair x comma y. So we indicate this functional dependence by writing that temperature is equal to a function of x and y. So it depends on the longitude and latitude. Similarly, the volume V of a cylinder depends on its radius and height, right? So in fact, we know that volume is equal to pi r squared times h. So we can say that volume is a function of the radius and height. And we can write volume is a function of radius and height and is equal to pi r squared. Okay, that's all it is. So just to form a little definition here, a function f of two variables is a rule that assigns to each ordered pair of real numbers x, y, and the set D, okay, that's the domain, a unique real number denoted by f of x, y. The set D is the domain of f, and its range is a set of all real values f takes on. Okay. So we often write this as z. So remember from one of our first lectures, the third variable in the three-dimensional coordinate system x, y, z. We often write this as z is a function of x and y to make explicit the values taken on by f at the general point x comma y. So we call the variables x and y the independent variables here because they're inside the function here, and z is the dependent variables. Okay, kind of like how x is the independent variable here and y is the dependent variable here when we're looking at functions of a single variable. All right, let me show you an example of this. Okay, in regions with severe weather, we introduce something called the wind chill index. Is often used to describe the apparent severity of the cold. Okay, the index W, all right, so that's wind chill, is a subjective temperature that depends on the actual temperature T, so it depends on the temperature T, and the wind speed V. Okay, so F, this wind chill, is a function of two things, temperature and wind speed, and we can write it as this. Wind speed is a function of temperature and wind speed. All right, so this table here records values of W compiled by the U.S. National Weather Service and the Meteorological Service of Canada. So you can see here. So we have the actual temperature and the wind speed. Okay, and these are then what we call, going back, the wind chill index, these numbers in here. Okay, so for instance, the table shows that the temperature of -5 degrees Celsius and a wind speed of 50 kilometers per hour, then subjectively it would feel as cold as a temperature of -15 degrees Celsius with no wind. So here's what you did. Temperature, wind speed, then that's the value it takes on, -15. All right, we want to expand this concept next talking about graphs, so how you visualize functions of more than a single variable. So another way to visualize the behavior of a function of two variables is to consider its graph. So if f is a function of two variables with domain D, then the graph of f is a set of all points x, y, z in the three-dimensional coordinate system, such that our z variable is a function of x and y. It depends on it, and x and y is in the domain here. So just as the graph of function f in one variable is a curve c with equation y is equal to f of x, the graph of the function of two variables is what we call a surface S, with equation z is a function of x and y. So it can just look like something like this. Okay, we can visualize the graph of S, the surface of F, lying directly above or below its domain D in the xy plane. So here are the allowable inputs, right, in the domain, and then this is the point on the surface up here. Okay, this is the z value right here. All right, let's do an example real quick. All right, let's sketch the graph of something g of x is a function of x and y is equal to the square root of 9 minus x squared minus y squared. All right, so the graph of this equation, I'm just going to change this g of xy to be z, okay, to be equal to our function. What we're going to do is we're going to get rid of the radical. We're going to square both sides to obtain the following. And then I'm going to move the variables all over to one side. So I have x squared plus y squared a little bit of a typo here, plus z squared is equal to 9. Sorry, that's a little bit of a typo. Which we recognize as the equation of a sphere, right, with the center being the origin, and it has a radius 3, because this is r squared. All right, but since z is greater than or equal to 0, all right, like you can't take the square root and get a negative, the graph of g is just the half of the sphere, the top half of the sphere. All right, let's just do real quick talk about functions of 3 or more variables. So you don't just have to have 2 variables. We'll go on and talk about functions of 3 variables. So a function of 3 variables, f, is a rule that assigns to each order triple, okay, this x, y, z in the domain of the real number of the 3-dimensional coordinate system, just a unique number denoted by f of x, y, and z. Okay, so for instance, the temperature T at a point on the surface depends on longitude and latitude, and then actually like what time of day it is. So for example, at the time of this recording, it's about 9:30 in the morning. It's going to be a different temperature around 12:30 in the afternoon. Okay, so we can write that the temperature depends on the longitude, latitude, and then the time of day. You can even expand this out, right, like day and then the month of the year and so on. So it can be more than 3 variables too. All right, let's just do an example real quick. Let's find the domain of f if f is order triple, okay, a function of 3 variables. It's a natural log of z minus y plus xy sine of z. All right, so the expression f of x is defined as long as the inside, this right here doesn't matter, xy sine of z. This is defined for all real numbers. So it's just the inside of the natural log. Okay, the inside of the natural log has to be greater than 0. Okay, so its domain is such case, okay, just flipping this over here, okay, that xyz is in a real number such that all that needs to happen is, this is a little bit of a typo, you'd add the y over, z is greater than y, okay? So this is a half sphere consisting of all points that lie above the plane, z is equal to y. All right, I hope this was a quick and nice, easy introduction for you to functions of more than 1 variable.